In this episode, we level up, moving from our deep dive into singularity algebra to confronting the monumental legacy of Stephen Hawking. We dissect two of his most thought-provoking papers, Living with Ghosts, 1997, and his final work, A Smooth Exit from Eternal Inflation, 2018. We tackle complex themes like higher derivative gravity theories, the eerie rise of ghosts in physics, the runaway nature of eternal inflation, and, where it gets wild, we test how far singularity algebra can push into this cosmic terrain. Can it model black holes, entropy, and the universe's endgame? Or do we hit the hard limits where real physics demands more? We wrap by reflecting on the responsibility of theory building, knowing when math is conceptual power and when it's not a physical law.
All right, so we're back. And diving deeper this time. Last time we really got into it with singularity algebra, all those concepts, really fascinating stuff.
Absolutely, a lot to unpack there.
Yeah, but now we're shifting gears a bit, taking on, well, a giant, really. Stephen Hawking.
Yeah, you could say that again. We're going to be looking at his work through the lens of singularity algebra.
Exactly, and we're specifically looking at two of his papers. First, there's Living with Ghosts from back in 1997.
Right, and then we'll jump way ahead to 2018, his final paper, actually, A Smooth Exit from Eternal Inflation, co-authored with Thomas Hortog, both of them.
Okay, so heavy stuff right off the bat. And we want to be clear, this is a serious discussion, Hawking's contributions to physics, to our understanding of the universe, they're monumental.
Absolutely. We're approaching this with the utmost respect.
Definitely. So let's start with Living with Ghosts. Now, this paper dives into some pretty complex territory, higher derivative gravity theories.
Mm-hmm.
Can you give us a little rundown of what that even means?
Sure. So in simple terms, higher derivative gravity theories try to expand our understanding of gravity. It's like taking Einstein's general relativity and adding some extra layers of complexity. These extra layers come in the form of, well, higher derivatives in the equations.
Higher derivatives. Sounds pretty technical.
It is. But the key is these higher derivatives are meant to help us understand gravity at extremely small scales, like the quantum level.
Right, and that's where the ghosts come in, right?
Exactly. The problem is, when you start working with these higher derivative theories, especially in more than 2 dimensions, you run into these things called ghosts. And they're not the friendly kind.
So, no Casper.
Not quite. In physics, ghosts are basically unstable modes in the theory. They show up as negative norm states.
Negative norms.
Yeah, it's a bit weird. Imagine a particle having negative energy. That's kind of what we're talking about. It throws everything off. And it leads to all sorts of problems, like violating unitarity.
Unitarity?
Yeah, it's kind of a bedrock principle in quantum mechanics. It basically means that probabilities always have to add up to 1. 100% certainty that something will happen. Ghosts mess that up.
So these ghosts, they're like glitches in the system.
In a way, yes.
Yes.
And that's where we can start to see the connection to singularity algebra. We've talked before about how singularity algebra deals with system instability.
Right. Reaching those critical points where things break down.
Exactly. And ghosts, they're a sign of that breakdown happening in these higher derivative gravity theories.
Okay, so we're starting to see the link, but it's still pretty theoretical, right?
True. But Hawking and Hertog, they didn't just leave it at that. They actually proposed a specific example. They looked at what's called a fourth-order scalar field theory.
Fourth order.
Yeah, meaning it involves fourth derivatives. So in this theory, they have this equation, a Lagrangian actually, that describes how the field behaves.
Okay. And they use this to show?
They show how those ghosts pop up. Basically, by rewriting the equation, they isolate a specific part of the field, and that part has a negative sign in front of it.
The negative sign again.
Yep, that's the hallmark of a ghost. That negative sign basically flips the energy of that part of the field, turning it into a ghost. And this ghost, just like we said before, it creates all sorts of problems for the theory, makes it unstable, makes it unpredictable.
So how do we deal with these ghosts? Do we just ignore them?
Well, Hawking and Hertog proposed a rather radical solution.
Yeah.
They argued that the way we're looking at these theories, the so-called canonical approach, it might be part of the problem.
We're looking at it the wrong way.
Potentially, yes. They suggested that we should switch to a different framework called the path integral formulation.
Path integral formulation. Something tells me there's math involved.
There's always math. But the basic idea is, instead of focusing on specific points in time, the path integral considers all possible paths a particle could take between 2 points. It's kind of like looking at the entire journey, not just snapshots.
Interesting. And this helps with the ghosts.
They believe so. By switching to this path integral approach, you change the way you define the quantum states. And that, they argued, could eliminate the ghosts.
So instead of directly confronting those pesky ghosts, we change the rules of the game.
You could say that. And this brings us to the really fascinating part. See, they use this path integral approach in what's called Euclidean space. It's a kind of space where time isn't treated as a separate dimension. Then, they use something called Wick rotation to go back to our normal space-time.
Okay, you're going to have to break that down for me a bit. Wick rotation. Sounds like something out of Harry Potter.
Think of it like a mathematical tool. It's a way to connect different kinds of spaces.
Yeah.
And it allows us to solve problems in one space and then bring those solutions back to the space we're actually interested in.
Clever. So they're basically taking a detour through this Euclidean space to tackle those ghosts.
Exactly. And what they found was, in this Euclidean path integral framework, you need to define quantum states differently. Instead of using the second derivative of the field, you only need the first derivative. And this, crucially, avoids the problem of ghosts.
So by changing the framework, changing how we define things at the most basic level, we can potentially get rid of those troublesome ghosts.
That's the idea. Now, this leads us to Hawking's later work, The Smooth Exit from Eternal Inflation paper. This one tackles a totally different but equally mind-boggling concept, eternal inflation.
Eternal inflation, it sounds kind of ominous.
It's a theory that says, well, inflation, that period of rapid expansion right after the Big Bang, it never really stopped everywhere.
It just keeps going.
In some regions, yes. The universe keeps inflating, creating more and more space forever.
Wow. And what about the regions where it does stop?
Those could be the seeds for what we see as our observable universe, and potentially countless others, creating a kind of multiverse.
Okay, so we've got this picture of a universe that's constantly inflating, creating more and more universes. But Hawking and Hertog, they weren't entirely convinced by this, right?
Right. They felt that this idea of eternal inflation, of this infinite multiverse, might be a bit too chaotic, too unconstrained.
Too much of a good thing.
Perhaps. They proposed that there might be a way for this Exactly. So they proposed that this deformed CFT, living in a lower dimensional space, could act as a sort of blueprint for the whole inflationary process. And that by tweaking this CFT, by deforming it in specific ways, we could actually bring eternal inflation to a halt.
So they're suggesting that we can control this vast cosmic process by adjusting something in a lower dimension.
Precisely. Now, this is where the connection to singularity algebra becomes even more intriguing. The need for a mechanism to end eternal inflation, to prevent it from going on forever. It resonates with the idea of recursive collapse in singularity algebra.
Right, we talked about that before. It's the idea that even in complex systems, there are inherent limits.
Exactly. And just like a computer program can crash if it runs out of memory, eternal inflation might need some kind of meltdown to prevent it from consuming all the resources of the universe.
A universal meltdown. But how does singularity algebra actually predict this ending of eternal inflation?
Well, singularity algebra has this built-in property called nilpotency. Basically, it means that if you keep repeating an operation, eventually it just stops. It reaches a limit. And if we think of inflation as this ongoing process of expansion, then singularity algebra suggests that this expansion can't go on forever. It has to hit a wall, a collapse point, a singular exit.
So the universe itself, according to this idea, has a built-in stop button.
In a sense, yes. Now, to back this up, Hawking and Hertog analyzed what's called the holographic measure. It's a way to calculate the probabilities of different outcomes in this eternal inflation scenario.
And what did their calculations show?
They found that the most probable outcomes are those where the universe's geometry is relatively simple, close to a sphere. The more complex, chaotic geometries, the ones you'd expect in an infinite multiverse, those were far less likely.
So a simpler finite universe is more likely than a chaotic infinite one.
That's what their analysis suggests. Now, stepping back and looking at both of these papers, Living with Ghosts and A Smooth Exit from Eternal Inflation, we can see some really interesting connections to singularity algebra.
Right. Both of them seem to be dealing with these ideas of limitations, of collapse, of systems breaking down when they go too far.
Exactly. We can think of both ghosts and eternal inflation as examples of what we might call non-reversible resource overflows. Meaning that they represent situations where a system keeps pushing beyond its limits, trying to use more resources than it has, and ultimately leading to a breakdown.
Okay, I'm seeing the connection. So you're saying that singularity algebra with its focus on limits and collapse, could be the key to understanding these seemingly unrelated phenomena.
That's the idea. And it might go even deeper than that. Some physicists have even suggested that singularity algebra could be the foundation for a computational physics of black holes.
Black holes. Now we're really getting into the cosmic deep end.
Indeed. The idea is that black holes, with their incredible density and gravitational pull, might be the ultimate testing ground for these ideas of singularity and collapse, and that prime numbers, due to their unique mathematical properties, could play a crucial role in understanding black hole entropy.
Prime numbers and black holes. Who would have thought?
It's pretty mind-blowing stuff. And if we connect this to Hawking's work on soft hair on black holes, a concept dealing with information storage at the black hole's event horizon, we can even see parallels with Singularity Algebra's meltdown addition process.
Meltdown addition. Refresh my memory.
It's basically the idea that after a system collapses in singularity algebra, there's this residual capacity left over. And this leftover capacity, it could be analogous to the information carried by the soft hair on a black hole, like a trace of what was there before the collapse.
A fascinating concept, information surviving even after a system meltdown. And what about those nilpotent pairs in singularity algebra? We talked about how they lead to collapse, right? Is there anything similar going on in Hawking's work?
Actually, there is. It's a bit subtle,
Right.
but the idea of nilpotent pairs, where two opposing elements cancel each other out, it's reminiscent of how those ghost states, with their negative norms, can effectively annihilate real particles in quantum field theory.
So even in these seemingly disparate areas of physics, we're seeing similar patterns, similar limitations.
Exactly. And that's the beauty of singularity algebra and this idea of eternal inflation.
Okay, so how does singularity algebra fit in there?
So the paper calls it a conceptual theorem.
Okay.
If we think about Mn in the context of the early universe,
Okay.
where n is like the force making the universe expand super fast.
That's the inflationary push.
Inflationary push, exactly.
Yeah.
And m is like how much space-time can handle that expansion.
Okay.
Then our meltdown condition,
That's n sub 2 sub 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 1 sub is greater than m sub 1 sub.
yeah, that could actually stop that crazy expansion.
So it's like a built-in break.
Kinda, yeah.
Okay, walk me through that.
Okay, so as new parts of space start inflating,
Yeah.
that adds to the inflationary push, the n.
Okay.
But if that increase in push is way bigger
Yeah.
than the total capacity m,
Okay.
it could trigger a meltdown.
And that would end the eternal inflation.
Exactly. It's like popping a bubble.
Okay, so the algebra shows how eternal inflation might not be forever after all.
Right. And this connects to Hawking and Hertog's work on a smooth exit.
Oh, yeah, where they said infinite expansion might not be guaranteed.
Exactly.
That's pretty wild.
Right.
Yeah. So the simple algebra
Yeah.
is showing up in all these big physics questions.
It's kind of mind-blowing.
It is. And the outline mentioned something about the algebra itself being really solid,
Oh, yeah. So even though it has those weird properties,
like non-commutativity and all that.
Yeah.
It's not just random rules.
definitely not. It
Okay.
actually makes a lot of sense.
Okay.
It's what they call closed,
Okay.
meaning that if you do meltdown addition with any two things,
Uh-huh.
you always get something that's defined in the system,
Okay.
or you get sub-e-sub.
Right. So it's consistent.
Exactly.
Huh.
The rules are clear.
Okay.
So there's no confusion about how to use them.
Right.
And that absorbing thing with sub-z or sub.
Yeah, where it just sucks everything up.
Yeah.
Okay. What about that black hole area law thing?
Right. So that one's more of a loose connection,
Okay.
but it's still interesting.
So tell me.
So the source is saying there's a similarity
Okay.
between the black hole area law,
Uh-huh.
where the area of a black hole's event horizon is related to the square of its mass,
Okay.
and the m sub 2 sub term in singularity algebra,
Okay.
where m is the capacity,
Yeah.
which is kind of like the size of the system or how
Right.
much information it has.
Like the mass of a black hole.
Yeah. And then the collapse to sub-sub
Yeah.
is like the formation of that event horizon.
So the algebra is reflecting that relationship between area and mass.
Yeah, in a way.
That's really cool.
Okay, so lastly, let's go back to Hawking's Living with Ghosts.
Oh, yeah. The ghost states again.
So the papers connect singularity algebra to that discussion
How so?
by saying that those higher derivative gravity theories, the ones Hawking looked at for quantum gravity,
Uh-huh.
they often have these unstable ghost modes.
Right.
And the idea is that singularity algebra with its whole collapse thing
Yeah.
might help us understand what happens.
When those ghost states cause problems.
Exactly, like when you have too much stuff and the system breaks down.
Okay, so the algebra is a way to model the result of those ghost states.
Yeah, even if it doesn't explain the ghosts themselves.
Got it.
And It's similar to what Hawking was talking about.
With those infinite recursive failures.
Yeah, like a chain reaction of failures leading to collapse.
So the algebra could be like a simplified way to describe that.
Exactly.
Yeah, this has been a lot.
Right.
It's easy to get caught up in all these connections, and I'm sure some of our listeners out there might be thinking, wait a minute, is singularity algebra like the master key to the universe?
All right, the key to everything.
Like, does it unlock all the mysteries from the tiniest quantum jitters to the vastness of the cosmos? And that's exactly why we need to kind of take a breath here.
Yep, step back a little.
Yeah, and ground ourselves a bit. Because as cool and compelling as these overlaps are, it's really crucial to balance that enthusiasm with a healthy dose of reality.
Absolutely. So today's deep dive, it's not about finding even more connections. It's about really understanding where the limitations of applying this singularity algebra directly to the physical universe, those limitations start to show up.
Yeah, where the rubber meets the road, so to speak.
Exactly. We need to be clear about where this mathematical framework is a powerful tool for thinking conceptually, and we're interpreting it as a literal physical model, especially when we're talking about real black holes, and predicting fundamental physics requires a much more careful and cautious approach.
Okay, so let's break this down.
That's it.
It feels like there's a crucial piece missing when we try to directly map the algebra onto physical reality.
This difference between having a mathematical model and having a fully fleshed out physical theory. When we talk about the real world physics, particularly gravity and the very structure of space-time, our most successful descriptions, those rely on something called a metric.
Okay, a metric.
Yeah, think about something like the Schwarzschild solution, which describes a non-rotating black hole. It uses this very specific mathematical structure called the metric tensor to tell us about how space-time is curved around that black hole.
Okay, so the metric is telling us about the shape of space-time.
Exactly. It defines how distances and angles are measured within that warped fabric of reality.
So it's like a map of the distortions caused by the black hole's gravity.
Exactly, and that's where the disconnect lies. Singularity algebra, it talks about these m's and n's, resources and demands, but it doesn't inherently describe that underlying geometry of space-time, that curvature, in the same way that Einstein's theory of general relativity does with its metric tensor.
So it's like the algebra is describing this breaking point, this mellage, but it's not telling us about the stage on which that breakdown is actually happening.
A perfect analogy. It's like the algebra is giving us the drama, but not the setting.
Yeah, exactly. And that's a pretty big omission when we're trying to talk about real physical phenomena.
Absolutely. And here's another key point. Those rules of singularity algebra, the way those m's and n's interact and lead to that meltdown, they haven't been derived from the fundamental principles of general relativity. There's no clear mathematical pathway that takes us from the core ideas of gravity and space-time curvature to the operational rules of the algebra. It's like having this amazing recipe that tells you exactly how to combine ingredients to bake a delicious cake.
Okay, I like where you're going with this.
But that recipe, it doesn't explain the underlying chemical reactions that are actually making those ingredients interact the way they do to create that cake.
So the algebra might give us a tasty result, but we're missing the chemistry behind it.
Precisely. And that's a crucial point to keep in mind when we're assessing the algebra's ability to really describe the universe at a fundamental level.
And the sources we looked at, they even brought up Hawking radiation as a prime example, right?
Yes, Hawking radiation, absolutely.
That's a fundamental aspect of how we understand black holes. But it seems to operate on a level that the basic singularity algebra just doesn't touch.
Right. It's like the algebra doesn't have the right tools to even see Hawking radiation.
So tell me more about why that is.
Well, Hawking radiation, it emerges from those deep principles of quantum field theory applied to the curved space-time around a black hole. And it involves some pretty intricate concepts.
Okay, hit me with them.
All right, so we've got things like Bogoliubov transformations, which essentially describe how different observers perceive the vacuum state in quantum field theory.
Okay, the vacuum state.
Yeah, and then we're also talking about the very structure of that vacuum, how it behaves in a strong gravitational field. These are core ideas from quantum field theory, a whole framework dealing with the quantum behavior of fields, and they're just not built into the foundation of singularity algebra as we currently understand it.
So it's like the algebra is missing a whole sense, a whole layer of reality that's crucial for understanding something like Hawking radiation.
Exactly. It's like the algebra doesn't have the eyes to see those quantum fluctuations in space-time that are giving rise to Hawking radiation.
And this is where things get really interesting to me, because while the idea in the algebra of a threshold being crossed and leading to an irreversible collapse, that does kind of echo the formation of a black hole.
Yeah, the point of no return. Precisely. It grasps this conceptual similarity, this idea of reaching a point where there's no going back. But it's not a direct replacement for or a fundamental explanation of the incredibly complex physics that actually governs how black holes are born, how they live, and even how they eventually evaporate.
Okay, so black holes are more than just a meltdown of resources in this algebraic sense.
It seems that way.
What about this concept of entropy, which is so deeply connected to black holes and was something we touched on before when we were talking about the algebra's meltdown boundary?
Yeah, entropy, that's a really important concept to consider here, and it raises a crucial question about just how deep the connection between the algebra and black holes really goes. There's definitely a conceptual resonance between the algebra's meltdown boundary and the formation of a black hole's event horizon. And you could even draw this loose analogy where the meltdown capacity in the algebra might correspond in some way to the black hole area law.
The bigger the black hole, the more information it can hold?
Exactly. It's like the event horizon acts as this information storage budget.
That's a neat parallel to draw with the algebra, the capacity to hold information being linked to this threshold of no return.
It is a neat parallel, isn't it? But here's where things get more complex. The sources we're diving into, they emphasize that black hole entropy, particularly as it's been explored in Hawking's later work involving this idea of soft hair, these subtle quantum properties at the horizon. It delves into a much deeper quantum territory.
Quantum territory. All right, so we're going deeper down the rabbit hole.
Exactly. And this deeper level, it potentially involves these intricate mechanisms for information storage right there at the horizon level, maybe linked to mathematical structures like the Virasoro algebra, which describes symmetries at the horizon, like conformal symmetry.
Okay, those are some pretty heavy-duty concepts.
They are, and the key takeaway here is this. While singularity algebra can model irreversibility, akin to horizon formation, it doesn't inherently capture these intricate quantum details about how information might be encoded or stored at that fundamental level.
So while the algebra can show us a system hitting that point of no return, it doesn't give us the quantum rulebook for what's happening at that boundary in the same way that these theories of black hole entropy are trying to do.
That's a great way to put it. The algebra is giving us the big picture, but not the quantum fine print.
Okay, so we've seen that the algebra might not be the perfect tool for understanding black holes and their entropy. But what about other areas of cosmology like eternal inflation? Does it hold up any better there?
That's another crucial area to examine. And one of the key differences that jumps out is the lack of any real sense of physical scale within the algebra. It operates with these abstract ideas of resource and demand, but there are no inherent units of time or space built into the framework.
So no meters, no seconds, nothing like that.
Exactly. And in physical theories, units of time and space, those are absolutely fundamental. They're essential for making any kind of quantitative prediction and for describing the dynamics of physical systems.
Because in the real world, things happen over a certain amount of time and within a certain amount of space.
Exactly. Those units allow us to answer questions like, how long will this event take? Or how big is that object?
Yeah.
Singularity algebra in its current form, it just doesn't have these fundamental building blocks.
And this lack of inherent units becomes particularly important when we start thinking about these cosmological models like eternal inflation, which, as we discussed before in the context of Hawking's work, might have had a smooth exit.
Precisely. The actual physics of eternal inflation involves these quantum tunneling events and these random or stochastic processes that occur within something called scalar field potentials. Think of these potentials as energy landscapes that govern the behavior of fields in the very early universe.
Okay, so these scalar fields are like the actors and the potentials are the stage they're performing on.
A great analogy. And the dynamics, the action on that stage, it's driven by quantum decay probabilities and how those probabilities influence the ongoing inflationary expansion and how it might eventually stop. These are specific physical mechanisms operating within a quantum field theory framework, and they're not directly modeled by the algebra's concept of resource overload leading to a meltdown-like state.
So while the algebra might conceptually model the end of eternal inflation as some kind of ultimate resource limit being reached, the underlying physical reasons for why that happens, the quantum fluctuations and the specific shape of those energy landscapes, those are quite different.
Exactly. The algebra can give us this very high-level abstract picture of reaching a limit, but it doesn't provide the detailed physical mechanisms that physicists believe are actually governing the dynamics of eternal inflation and how it might have ended.
Okay, so it seems like we've spent a fair amount of time talking about what singularity algebra isn't, It's not a direct replacement for our understanding of gravity based on metrics. It doesn't fully capture the complexity of black hole entropy, and it doesn't have these built-in units of space and time that allow it to directly explain phenomena like eternal inflation.
That's a fair summary.
But the sources we looked at, they also made it clear that this algebra isn't just some flimsy idea. It holds its own as a legitimate mathematical framework, right?
Absolutely. Despite these limitations when it comes to direct physical modeling singularity, algebra stands as a mathematically coherent and self-consistent framework. It has some well-defined and interesting properties that make it worth exploring further.
Okay, so tell me about some of its strengths.
Well, for instance, it exhibits closure, which means that when you perform operations within the algebra, the results you get are still within the defined set of the algebra, or you end up in that consistent meltdown state. It's like the algebra has its own internal logic, and it sticks to it.
So even though the algebra might not be a direct physical theory of black holes, it can still serve as a valuable algebraic model that resonates with certain high-level concepts from black hole physics and cosmology.
Exactly. It's like finding a similar pattern in completely different fabrics. It hints at some underlying connections or principles that might be at play across different domains.
And this brings us to a really critical point that's emphasized in the sources, the danger of overstepping the mark of making claims about the algebra that go beyond what it can actually justify.
To claim that singularity algebra directly models real black holes in all their quantum gravitational complexity, or that it predicts fundamental aspects of physics without a much more rigorous and well-established mapping to our existing verified theories, that would be a significant overstatement.
It's like saying because a particular metaphor helps us understand something conceptually, that the metaphor is actually the thing itself down to every last detail.
Precisely. We need to remember that singularity algebra at its current stage is best understood as a mathematical model that captures certain high-level similarities with these very complex physical phenomena.
So to sum up, it seems like we've learned that while singularity algebra provides this compelling mathematical framework for thinking about irreversible collapse, and it shares some intriguing conceptual overlaps with things like black hole formation and the possible end of eternal inflation, it faces significant limitations as a direct model of these physical realities.
A good summary.
The absence of a metric, a deeper accounting of quantum entropy and inherent units of space and time, all of these mean that it can't simply replace or fully explain our current physical theories.
Agreed. It can model threshold-based collapse in a variety of systems and potentially hint at some underlying universal patterns of irreversibility. It encourages us to think about these complex phenomena from a different algebraic perspective, which can be incredibly valuable in itself.
It's like adding another tool to our theoretical toolbox.
Exactly. The ongoing quest to understand the universe, it's a multifaceted journey, and it often involves looking at things through multiple theoretical lenses. Maybe abstract models like singularity algebra, while they might not be the final answer, can play a crucial role in guiding us towards those new and more complete descriptions of reality. And that's the beauty of science. It's a constant exploration, a constant process of refining our understanding.
Indeed. Well, thanks for joining us on this more grounded but equally fascinating deep dive. Until then, keep those questions coming.
Keep exploring.
And never stop questioning.
Absolutely.